Now, in this lecture, we will see some examples of hypothesis testing. The first example, we have a normal random variable with expected value mu unknown and variance equal to 16. So we are assuming a random variable which has got expected value mu is unknown and variance is equal to 16. So we are told that the true value of mu is either 8 or 25. We do not know the exact value of mu. Expected value is unknown, but we know that the expected value is either 8 or 25. For some reason, we are inclined to think that mu is equal to 8, but we don't know for sure. The closer is the realization to 8, and more we would be willing to conclude that the true value is 8. Similarly, the closer the realization is to mu is equal to 25, and the more we would reject that hypothesis that mu is equal to 8. So we have got two hypotheses, either mu is 8 or 25, and we will calculate the expected value, and we will see how to determine whether the expected value is 8 or 25. How do we use the data to derive some meaningful procedure for inferring whether my data is supporting my null hypothesis of mu not is equal to 8, or is rejecting it in favor of the alternative hypothesis mu1 is equal to 25? If null hypothesis H0 is true, the realization x prime comes from this graph. It should come from this graph. It should fall within this bell-shaped curve graph. If alternative hypothesis H1 is true, the realization x prime comes from this graph. So the key intuition is how far away from 8 must the realization be for us to reject the null hypothesis that the true value of mu is 8. Suppose x prime is equal to minus 12. In this case, x prime is much more likely to come from random variable x, where x is a normal distribution having mean 8 and variance 16, rather than x random variable which has got 25 mean and 16 variance. Similarly, if x prime is equal to 55, then this value is much more likely to come from this graph where mean is 25 rather than this one where the mean is 8. The procedure is to choose a point C called critical value and then reject H0 if x prime is greater than C, while not reject H0 means null hypothesis if x prime is less than C. So we have got to find this value. If our realization value will be greater than this value C, then we will say it is our hypothesis, null hypothesis was wrong, or we will reject our null hypothesis, or if it is less than C, then we will accept it. If it is less than C, we will accept our null hypothesis. If our realization is greater than C, then we will reject our null hypothesis. What is the probability that we reject H0 by mistake? That is when the true type 1 error value of mu was actually 8. We have seen type 1 error, which is if we reject a null hypothesis that is actually true, then we have made a type 1 error. What is type 1 error? That our null hypothesis was true, but by mistake we have rejected it, and it is called alpha. And on the other hand, if we accept the null hypothesis when it is in fact false, then we have made a type 2 error, which is called beta. The point is to find this C in a meaningful way. So we will reject H0 if x prime is greater than c, while not reject or accept h naught if x prime is less than c. Therefore, this is nothing but the area under x, and for normal distribution, x is random variable, on the interval c, this critical value, and positive infinity. A sensible way of choosing c is to do the other way around. You choose the probability of rejecting h naught by mistake, then you compute critical value c. As we know that the probability of rejecting h naught by mistake is called type 1 error or level of significance or alpha. Hence, the steps of hypothesis testing are: at first, choose a confidence interval. This is the first step. Second step, find the point C corresponding to the interval alpha, means type 1 error, where we have rejected a null hypothesis by mistake. And having C, one only needs to compare it to the realization x prime from the data. So once you have got the value of C, what you need to do is that you just have to compare it to the realization x prime from the data. If x prime is greater than C, then we reject h naught, knowing that we might be wrong in doing so with probability alpha. Since we want the error to be as low as possible, the most common values used for alpha are 0.01, 1%, 0.05, 5%, and 0.1, 10%. Suppose we choose significance of 1%, means 0.01, for our example. The first thing to do is to find the value of x prime at 0.01 probability. So, how do we find this value of x prime? Z is equal to x minus mu over sigma. So, the probability that z is greater than 0.01 is equal to c minus u over sigma. To get the value of z from the table, we change greater than to less than, because the table gives the probabilities less than z. This table gives the probabilities less than z. So, p z is less than 0.99 is equal to c minus mu sigma. From the reverse lookup into the table, we find that z is equal to 2.33 at probability of 0.9901. We try to find this value in the table. Here it is 0.9901, which we have calculated over here, 0.99. 0.99 is here. So, if we reverse lookup, means we have to look at the value of z over here. We have tried to find the value, and then we try to find the value of z, which is 2.3 over here in this case, which is 2.3 here. So, z is equal to 2.33 at probability of 0.9901. Hence, 2.33 is equal to c minus 8 over sigma. Sigma is the standard deviation. We know the variance. So, sigma is equal to under root sigma square, which is equal to 4. So, now we just replace, now just we put the value of sigma in the equation, and finally we get c is equal to 17.32. So, at significance level 1%, the value of c is equal to 17.32. Now we test some value of x. Suppose that we get x prime is equal to 15. Is x prime is equal to 15 far enough from mu 8 to lead us to reject null hypothesis? We compare this x prime with our critical value. X prime is 15 and our critical value is 17.32, which means that we accept the hypothesis that mu is equal to 8. Suppose we run the test with another realization of x, say x prime is equal to 20. We are assuming these values of x prime. And here we can see that this realization value is greater than critical value 17.32. Therefore, it is rejected. So, the value of realization of x will decide whether we have to accept the null hypothesis or reject it. Note that when rejecting H naught, we cannot be sure at 100% that the true value of the parameter mu is not 8. Similarly, when we fail to reject H naught, we cannot be sure 100% that the true value for mu is actually 8. What we know is only that in doing the test several times, we would mistakenly reject mu is equal to 8 when alpha is equal to 0.01 probability. So what is the probability of false rejection? Is it that mu is 8? It is 0.01. Similarly, the critical value for alpha is equal to 0.05 and alpha is equal to 0.1. We calculated the values C is equal to 17.32, 14.56 and 13.12. The same way we have calculated the value of C for alpha is equal to 0.01. Again, assuming that the realization of x is 15 and alpha is equal to 0.1, do we accept the hypothesis that mu is equal to 8? The answer is no, because 15 is greater than 13.12. The higher the probability that we accept in rejecting H naught by mistake, and the more likely it is that we reject H naught. We can find a probability P so that we will reject H naught for alpha greater than P. Let's compute the probability P x prime is greater than 15. So, probability that our random value x is greater than x prime, which is 15, we have supposed, then P is equal to Z is greater than 15 minus 8 over 4, which is equal to 1.75. And when we subtract this value to be able to look into the table, we subtracted from 1 and we get 0.9599. So at 0.9599, we see that the probability, the value of Z is 1.7. So P is equal to 1 minus 0.9599 is equal to 0.0401. If x prime is less than C, then probability P is greater than alpha. In that case, do not reject the null hypothesis at 0. If x prime is greater than C, then P is less than alpha. In that case, reject the null hypothesis at 0. In our example, 15, x prime is less than 17.32, means 15 is our x prime value and 17.32 is our critical value, and consequently 0.0401 probability is greater than 0.01 alpha. So, in our example, we have matched this case, this condition over here. This condition is met. So, therefore, H naught is not rejected and this null hypothesis is accepted. Now, what is power of a test? The power of a test is the probability that we correctly reject the null hypothesis. It is expressed by the letter pi. The probability P is called p-value. The p-value is the lowest level of significance which allows to reject null hypothesis, H naught. The lower p and the easier will be to reject a null hypothesis, since we will be able to reject null hypothesis with lower probabilities of rejecting it by mistake. In other words, the lower p and the more confident you are in rejecting H0. Now we look at another example, chocolate bar example. Suppose a machine produces chocolate bars having the average weight of 5 grams. Suppose a person claims that the machine does not produces the chocolate bars having 5 gram of weight on average. The machine is supposed to produce the chocolate bars of 5 gram, so we assume that our null hypothesis H naught is on average the weight of the chocolate bars is 5 gram. Mu is equal to 5 gram. This is mu naught. The alternative hypothesis, which opposite to the null hypothesis, is that the machine does not produce the chocolate bars of 5 gram on average. So, our H1 is equal to is that mu is not equal to 5 gram. Possible outcomes are reject H0 means we reject this null hypothesis. Fail to reject null hypothesis means we accept this null hypothesis. Let's take the sample of 550 bars. Take the average weight of the 50 bars. Now we have to decide to reject or fail to reject the hypothesis based on the average weight of the 50 sample bars. Significance testing example. A pharmaceutical company wants to test the effectiveness of the new anti-hypersensitive drug that they are developing. A group of n is equal to 25 volunteers is selected with a mean systolic pressure of 150 millimeter of mercury with a standard deviation of 25 millimeter of mercury. The company wants to see whether the new drug can bring the systolic pressure below 140 millimeter mercury. We have to design a test to determine whether the drug is effective at a significance level of alpha is equal to 0.01. In other words, we have to find estimated mean at alpha is equal to 0.01. We will assume that the systolic pressure is a Gaussian distributed random variable x with mean mu 25 is equal to 150 and standard deviation sigma 25 is equal to 25. Hence, the sample mean mu 25 of systolic pressures after taking the drug is Gaussian distributed with mean 150 mmHg and standard deviation is equal to 25 divided by under root 25 is equal to 5. Therefore, we have to choose such a value of reject which should be at significance level is equal to 0.01. If the null hypothesis is rejected at significance level of 0.01, then we can conclude that the drug is effective in controlling systolic blood pressure. What is the procedure of hypothesis testing? Procedure for hypothesis testing is that, first of all, null hypothesis H naught must be carefully formulated. Second, define the experiment to be performed. Third, choose a proper test statistic. Fourth, establish the significance level alpha. Fifth, choose a value for type 2 error. And sixth, with alpha and beta specified, determine a suitable sample size n. So we look at an example of hypothesis testing. Diastolic blood pressure measurements were recorded for a patient on 10 different occasions. The pressure measurements are assumed to be Gaussian distributed. See, these are the measurements. They are assumed to be Gaussian distributed. We want to find whether these measurements support the hypothesis that estimated average pressure is less than 80 at the significant levels of 1%, 2.5% and 5%. So first of all, we calculate the estimated mu value from data which is 82.2 and standard deviation sigma is equal to sum of x minus x estimated x average value squared divided by n and then root is taken. So x minus x whole square, these values are calculated. Value of x minus x bar minus 4.2 and then it is squared. This is value of x minus x bar, 2.8. Then it is squared and so on. And finally, we get sigma, which is 115.6. Then we divide it by 10. And then we take the under root and we get sigma is equal to 3.4. We have to test if the pressure will be less than 80. So T is equal to C alpha minus mu naught divided by sigma, estimated sigma divided by under root n, which is student T distributed. The T values for 1%, 2.5% and 5% significance levels for n minus 1 is equal to 10 minus 1 is equal to 9 degrees of freedom from student T table are 2.821, 2.262 and 1.833 respectively. We can now formulate the composite hypothesis as null hypothesis at 0 is mu is less than mu naught is equal to 80, and alternate hypothesis is that mu is greater than equal to mu naught. For 1% significance level, T we have got it from this value from the table 2.821, C alpha we have to calculate minus 80 divided by 3.4. This is the sigma value which we have already calculated, and we know that we have got total 10 samples, so n is equal to 10. Then we have to do simple arithmetic. We get the final answer is equal to 83.033. Since H1 is equal to mu greater than H0, H0 will be accepted if this expected value mu is less than C alpha. Here mu expected value is 82.82, which we have already calculated here, 82.2, and C alpha is 83.3. So we will accept null hypothesis if this value, estimated average value, is less than this critical value. So it means H naught is accepted. For significance level 2.5, our H, estimated H value is 82.2 and critical value is 82.432. So in this case, still this value is less than critical value and we accept it. And for 5% significance value, we see that H mu is equal to 82.2, but critical value is 81.97. So in this case, we will reject it. So we will accept this hypothesis for significance level 1%, 2.5%, but we will reject it for 5%. So we can see that accepting or rejecting a null hypothesis depends on the significance level, what significance level you are going to assume. Example 2 of hypothesis testing. An energy specialist recommends that a homeowner could save at least $15 a month in utilities if energy appliances were upgraded. Before the upgrade was installed, the mean monthly utility expense was $255 with standard deviation of $17. After the upgrade, the mean monthly expenses for a 10-year period is shown below. So in first year, on average, we got $243, second year $252, next year $246, and so on. We want to test whether the upgrade has saved $15 a month at significance level of 1%, 2.5%, and 5%. We will assume that the utility expenses are Gaussian distributed and formulate the null hypothesis H naught as mean monthly expense is equal to $255, which is given in the question. This is our mu null hypothesis. And the alternate hypothesis H1 as mean monthly expense is 255 minus 15 because we are going to save $15 each month. This is what we assume. So our mu1 is equal to $240. This is our alternate hypothesis. If H naught is rejected and H1 is accepted at significance level of alpha 0.01, 0.025 and 0.05, then the homeowner would have saved $15 a month. The estimated mean of the average monthly expense is equal to, we just add up all these values and divide it by 10 because it is the rate of 10 years, and what we get is $243. So on average, it was $243 every month. And sigma is equal to 17. This is our standard deviation. Now, again, we have to find this value of C first, critical value. The simple hypothesis H0 is 255 and H1 is equal to 240 at significance levels of 1%, 2.5% and 5%. The corresponding Z values from Gaussian table are Z is equal to 0.01 is equal to minus 2.32, Z 0.025 is minus 1.96 and Z is 0.05 minus 1.64. We can see it from this Z table. When we have value 0.01, so for 0.01, this is the most closest value, 0.01, we have minus 2.32. For 0.025, we have minus 1.96, and for 0.05, 5%, we have value minus 1.64. For 1% significance level, when we calculate the value of C, after putting all the values in this equation, which we have done before, the answer is 242.53. And for significance level 2.5, C is calculated as 244.46, and for 5% significance level, C is calculated as 246.18. Since the estimated mean is 243 greater than 242.53, we conclude that the null hypothesis mu naught can be accepted at the significance level 1 with consequent no average monthly saving of $15. On the other hand, mu is equal to 243 is less than 244.47 and 244.47 is less than 246.16, and the null hypothesis is rejected at 2.5% and 5% levels. And the alternate hypothesis mu1 is equal to $240 is accepted, resulting in an average monthly savings of $15. So if our null hypothesis, if significance level is 1%, then we can say that we have not saved $15 after upgrading the appliances. But if significance level is 2.5% or 5%, then we can say that on average we have saved $15 per month.